Hi, everyone. My name is Myra Gonzalez. Today, I will present our research on new materials for clean energy technologies. Our work focuses on fuel cells. These are electrochemical devices that convert chemical energy directly into electricity, with only heat and water as byproducts. However, their performance is limited by a slow chemical reaction called the oxygen reduction reaction, or OR. To speed up this reaction, the best material is platinum. But platinum is very rare and very expensive. This is a major barrier for large-scale application. Therefore, our objective is to find a better alternative, a catalyst that is low-cost, stable, and efficient. We are investigating a class of materials called orthoferrites, with the general formula RFeO. In our study, R is a rare earth element. We chose three different ones: lanthanum, neodymium, and erbium. These elements have different sizes. Lanthanum is the largest, and erbium is the smallest. Our goal is to understand how this change in size affects the material's structure, its physical and chemical properties, and most importantly, its ability to perform catalysis for the oxygen reduction reaction. So, how did we create these materials? We used a simple and effective method called solution combustion synthesis. This method is excellent because it is fast, energy efficient, and easily scalable for industrial production. To test their performance, we used a standard 3-electrode electrochemical setup. We created a catalyst ink and deposited it onto a glassy carbon rotating disc electrode. This allowed us to measure the material's activity for the ore in an alkaline solution. Now, let's look at what we found. First, we needed to confirm the structure of our materials. Our X-ray diffraction results show sharp, narrow peaks. This indicates that our materials have high crystallinity. Furthermore, the absence of extra peaks confirms that we successfully synthesized pure materials with the desired orthorhombic crystal structure. Now, for a key detail. If we look closely at the main peak, we see a clear trend. As the size of the rare earth ion decreases, from lanthanum to erbium, the peak shifts to higher angles. This is direct evidence that the crystal lattice is contracting, and the unit cell volume is decreasing, just as we predicted. Next, we looked at the morphology. The electron microscope images show that all materials are composed of agglomerated nanoparticles. Compositional analysis confirmed the correct elements were present, and mapping showed a very homogeneous distribution, which is a key advantage of our synthesis method. Other analyses confirmed the chemical bonds within the structure and showed a clear trend in surface area. Lanthanum had the highest, followed by neodymium, and then erbium. So, the most important question: how does this affect their performance? This is our most significant result. These graphs show the catalytic activity. While the lanthanum and neodymium materials begin the reaction at a similar potential, the neodymium-based catalyst achieves a much higher current density. This clearly shows that it is the most active catalyst of the three. In contrast, the erbium material shows very little activity. To understand why, we found that the superior performance of the neodymium catalyst is related to its higher electrochemically active surface area. This means more of the catalyst surface is actively participating in the chemical reaction, which boosts its overall performance. In conclusion, we have drawn several key points from this work. First, we successfully synthesized high-purity LFeO, NFeO, and RFeO orthoferrites using the solution combustion method. Second, we demonstrated that changing the rare earth element has a significant impact on the material's physiochemical properties and its catalytic activity. Our results identify NFeO, the neodymium orthoferrite, as the most promising catalyst in this series, due to its excellent properties and higher active surface area. Finally, our materials have a band gap of about 2.1 electron volts. This suggests they could be activated by visible light, opening an exciting new possibility for their use in photocatalytic applications, such as water purification or solar fuel production. This will be the focus of our future work. Thank you for your attention.